So last time we talked about substituted redox replacement, motivation, thermodynamics, etc. And we have shown that basically the trick is to conveniently use PPD monolayer as a reducing agent in redox or electrolysis deposition process, where we restrict the amount of platinum deposition by redox process with geometry. So if we say that we have PT coverage of the metal UPD plus metal P, which is typically a catalyst like platinum, then we get M plus P deposited on substrate, plus here, some substrate S, HKL, right? And this is substrate S, HKL, right? And we said that M usually could be copper, PV, bismuth, limonene, thallium, cadmium, etc. And usually P metal index is platinum, palladium, iridium, rhodium, ruthenium, etc. And this costs a lot of dollars, right? Okay, so and the process works very simply by just going in one beaker where we have copper, or let's say M ions. We stick our substrate, and the only requirement is that the M metal does deposit UPD layer on substrate. That's the first step. Then the second step will be to rinse this from any residual solution where we have MUPD monolayer on the substrate S. And then to go to a third solution which contains PP plus ions. Stick this, and what's going to happen is that there will be redox, surface redox replacement, and eventually what we will end up is the substrate surface which is decorated with two-dimensional clusters, or eventually completely covered surface with a 2D P deposit. Now there are variations in this execution. I'll talk about this a little bit later, where this could be automated, where you, instead of shuffling the sample, you could shuffle the solution where the sample sits, and then you just drain the solution and put some other solution and so on. Or there's a little bit different approach where we can do everything in one pot, but it's not exactly the same process. I'll explain the difference a little bit later. Okay, but what is important for you guys to appreciate is that thermodynamics explain to some extent why we get 2D, because we have this delta E SLRR because of this solution not having no PV ions or no M ions in the SLRR solution. Because of that, this goes really big, right? Because if you remember this expression, this ln where we have here a P activity, sorry, and here a M activity. If this goes to 0, this goes super big, and this goes super big, and in this expression for delta E SLRR, basically this goes super big, and when this is super big, you remember J is proportional to the exponent of some constant, and here is delta E squared. And if this is super big, right, this goes to 0, and this goes to 0, this is minus, so obviously this becomes super big too, and make story short, 1 over 0 is infinity, so this becomes extremely big, right? And we have huge nucleation rate, right? But we have a limited amount of deposit before, according to this stoichiometry, because this data could be between 1 and 0, right? So you can only get up to a monolayer whatever of P. Because you have a huge driving force for nucleation, you will get gazillion small clusters which are actually reduced to the ultimate size of two-dimensionality, right? We covered that, right? Well, it turns out, even if I add some M here, Mn plus ions, I still get 2D. Deposit. So, obviously, if you do it without M, you can employ thermodynamics to explain why you're getting two-dimensional monolayer. But the catch is that if you put some M plus ions into the SLRR solution, you're still going to get some two-dimensional deposit. And so that's number 1 question mark. Number 2 question mark is that when you compare morphology of the deposit between copper 2 plus copper 1 or copper 2 plus oxidation states, which means, you know, in this particular reaction, you know, if you have a copper UPD, it can go to copper plus or copper 2 plus, depending what kind of acylation you have, whether you have sulfuric acid or you have chlorine ions in the solution. You know, copper 1 could be stabilized and so on, but the bottom line is this: if you employ thermodynamics, or if you look just at PB, you know, as a UPD metal, the thermodynamics predicts certain ratio in nucleation rates between these, but when you do employ STM, you don't see that exactly being predicted by thermodynamics. So that's a question mark number 2. Okay, so then becomes a puzzle. Why we are getting to the deposit? So when we published this paper, I thought, man, I know everything. But I don't. It turns out there's a lot of more things to be discovered, which made this whole story much more enjoyable. First of all, thermodynamics is good to discuss certain processes which happen relatively slow, which means you go from one state to another slowly, almost through a bunch of small equilibrium states, and eventually somehow thermodynamics could be detached from kinetics, because kinetics is so slow that it's really not affecting too much of the process. But that's not the case here. This reaction is actually instant, very fast. And that brings us to a topic of this lecture, which is called kinetics. But I'm not going to talk about kinetics of the deposition, but I'm going to talk about nucleation kinetics during deposition of SLRR. So this lecture is nucleation kinetics of deposition via might want to know a little bit more about nucleation kinetics and so on. Okay. Well, let me tell you why. So I'm going to give you an intro for why we're talking about this, because ideally the catalyst morphology when you talk about monolayer, catalyst on substrate, whether you have this size of the cluster or this size of the cluster, they're still 2D. But there is something important that you have to appreciate in this particular geometry, and this is two-dimensional Laplace pressure, or we call this finite size effect. So, in very simple words, if you nucleate small clusters as a catalyst material, they will act different than the big clusters, and the activity will be significantly different. So it does matter whether you're generating big or small clusters for particular chemical reactions, if you're going to use one of the catalyst. The difference could be so huge that, for example, at certain conditions when you have these small clusters, maybe 3 nanometers square, and these 30 nanometers square, you would probably need about 300% more area of this catalyst than these in order to get the same rate of the reaction. And so, having said that, let me give you some idea. This is not part of the class, but it's important for you to understand why we are talking about nucleation kinetics. So, what you see here is basically different applications of the monolayer catalyst. I just put some, whether it's chlorine production, water electrolysis, metal layer batteries, production of isotopes, fuel cells, etc. Bottom line, what we talked last time, you see what? What do you mean? Peter, just turn the camera. Bottom line is that what you see is that if we do the right thing, then this exponential increase in the price should be mitigated by the smart use of material. Now, unfortunately, there's also a lot of politics involved, so not necessarily only science can solve the problems. But the idea is that if we can go to monolayer configuration, you can see here, for example, we can generate catalyst material where you have only one layer of platinum on palladium, for example, which is the best oxygen reduction catalyst up to date, for example. There's no more active one. And the reason is that there's a synergy between electronics effects, stress, etc., strain effect, and so on. And so basically, monolayers could be tuned in terms of their catalytic activity. Okay. Now, when we're talking about the monolayer catalyst materials that you produce by this deposition, the SLRR, usually we talk about different, I would say, nanocluster size distributions. As you can see, we can talk about monolayer, which has a coverage less than 1, because the surface is not 100% covered by these clusters. And you can say they can have a different size, shape, etc. distribution. Okay? And that depends how we make it. Then, if I get a good student, I can show you that you can also get monolayer, continuous monolayer configuration of platinum on a substrate if you know what you're doing. But you can, but it's still coverage less than 1. And then you can end up with this type of configuration where you have a surface completely covered, coverage 1, but it consists of Brazilian organic clusters with certain shape, size, and shape distribution. All right. Now, when I say size and shape, let me just go quickly and tell you a few things. These are some theoretical calculations on the right, or actually on the left side. It shows you how the overlay, which is the monolayer, and the substrate, which is on the left side, have their electronic functions, or basically electronic overlaps, affect each other. And so what you see here is the combination in each of these squares at the particular column and row, and row is the substrate, gold, for example, and iron monolayer, cobalt, nickel, ruthenium, da. And so you can see what is the red that tells you that the center of the energy of the deep end goes up towards the Fermi level, or blue means going down. White means not really a big change. Now, why is that important? Because if you put the monolayer on different substrate due to the electronic effect and some other things like strain, you can actually tune the activity by the substrate, choice of substrate, and that monolayer, and you can make monolayer more reactive. If you see red, that means more reactive, meaning higher activity of the catalyst, because the electron density is pushed up towards the Fermi level, which means more electrons are available for absorption or reactive overlap with some kind of a, reactants. Or it could be pushed down, which means less electron density will be on the surface available for catalytic action. Okay, so you get the theory, right? Then the people also did some measurements. This is from Victor Kolb's group, and they nicely show that, for example, the epitaxial strain, which is defined here as a misfit between the lattice parameters of the substrate and the monolayer you put, actually controls the activity in some sense of these palladium monolayers, which are deposited on different substrates. So obviously the theory kind of agrees well with some things that we can measure, but what they don't tell you here is that this all applies to the situation where you have a perfect monolayer like this, sitting on your substrate with the epitaxial match, where the strain is known due to the epitaxial misfit and the electronic, mixing and stuff could be easily addressed by DFT. What they don't tell you is that in reality there's only a few systems you can make this. In reality, what you have is this, which is the finite clusters, small 2D clusters. And these 2D clusters have a strain map which is completely different than the one that we expect for this, because due to the two-dimensional Laplace pressure coming from the side of the cluster, because there's no pair bonding on the perimeter, they don't have anybody to hold, so they squeeze towards the center. So you have a huge compression at the perimeter, and then compression is slowly released as you're coming down towards the center of the cluster. So the average strain in this cluster is quite different than the strain predicted by epitaxial misfit. And so again, you know that if the strain is positive, we are shifting the deep end center of the energy towards the Fermi level, increasing reactivity. But the bottom line is that in reality, due to this two-dimensional finite size effect, we will always have this, because the average strain in the cluster will be always compressed. So they don't tell us. So when we calculate this and we evaluated this effect, now that was the eureka moment, because I started understanding certain issues with this whole business here. When I make my catalyst on Monday versus Wednesday, why they don't perform the same way. Monday I get banged up on the bars, I don't see where I mix the solutions which are not necessarily right. By Wednesday I sober up, I start doing things right. Turns out that kind of benefits the catalyst performance. Alright. Here's what I show you is the strain in this cluster as a function of the size of this cluster, and you can see for ultimately big clusters the strain is equal to the one that we expect from epitaxial misfit for the monolayer. But for relatively small clusters with a radius, let's say below 10 nanometers, you can see it significantly departs from what we expect for the continuous monolayer. All right. And so, then if you look at some DFT stuff, you can see that although DFT is done for really small clusters, which are not realistic, but you can see that the surface strain, which means to be measurable strain in these clusters, follows basically the shift in the D-band. Okay, so bigger clusters supposedly are more active because the D-band goes up towards the Fermi level. Now, when we did some real measurements, and this is the normalized exchange current density for the hydrogen oxidation reaction. I don't know if you see my pointer, but that's not important. This is some kinetic parameter that we evaluate for the catalyst, which has different mean platinum cluster size. What is the mean platinum cluster size? Is that we measure all the clusters, we get a distribution, and the mean is this. So it's representative, kind of, not really average, but representative value of the whole clusters on the surface. And so when we represent what we measure for the particular catalysts that are purposely synthesized using different conditions, we are the approach we described, we see significant difference in the activity. For example, the relatively small clusters or population dominated by small clusters, the exchange current density normalized per cover is 0.2. Yet, for the ones that are about 40 square nanometers, it's about 0.6. So it's a ratio of 3 times, 300%. What that really means is that if I want to have the same kind of activity, I have to use 3 times more area of this catalyst in order to make up for the same activity that the bigger clusters have. Now, 3 times means money, because remember, the whole idea of the monolayer concept is to come up with a reasonably simple, executable process for synthesis of the monolayer catalyst because we want to save the money. Here you are, you're trying to save the money, but if you don't pay attention to how you synthesize your catalyst using this approach we discussed, you can go off 300%. And 300% when you're talking about some serious, let's say, production of the catalyst for fuel cell cars, could be difference between 100 million versus 300 million. 300 million means 300 million less profit, lower salaries, and so on, okay? And here, you know, if we look at this hydrogen oxidation reaction, you can see that the D-band of the platinum scales nicely linearly with the strain. And the same thing, you know, we see experimentally. Okay. The second example of this whole business, why the size of the cluster is important, is shown here, where we have platinum monolayer of palladium, and obviously it's 100% coverage, but you can see the clusters are about, you know, 4 nanometers diameter, which is about 52 atoms, and we can exactly calculate the strain state using DFT. And this is strain path calculated by DFT. And then we can find the average strain in this cluster, which is about -3%. That is not the strain that's supposed to be by epitaxy, which is a little bit less than -1%. It's significantly different. And the worst thing is that if we do some CO absorption, just to explain what we see, is that this is our platinum and this is our palladium. If this activity of the palladium monolayer on platinum is dominated by the electronic effect, we should see in between these two peaks the strength of the CO absorption bond. However, we see the strength of the absorption bond shifting behind platinum, which tells us it's even weaker than it's supposed to be. Why is that? Well, if you do DFT of this same problem, it turns out that if you just simply think you have a strain in the cluster that is equal to the epitaxial one, which is here,
the calculation shows you that your basically vibration bond should be in between platinum and palladium, which is okay. That's what we thought initially. But it's not behind, it's not higher than palladium. But when you put the strain in the cluster that we know comes from the finite size effect, then we recover the results that you see experimentally. All right, so that was second Eureka moment. And then we started fantasizing. Because we're good at what we do, we said, what if we do first SLRR and we put ruthenium on gold? This is the first thing. Then we take this, and instead of using it as a catalyst, we do a second step UPD, but we only put UPD monolayer a fraction, which basically just decorates these ruthenium clusters. It turns out lead comes down not on the gold first, but first on the defects, which are basically these edges of the ruthenium clusters. This is what you see here when you analyze the UPD on ruthenium modified gold. You can see how the initial ruthenium clusters grow in size because the lead atoms starts to pack around the edges, right? But the cool thing is, then instead of putting the whole monolayer of lead, you stop right there when only edges of the ruthenium clusters are modified with lead. Take this out, and then you stick in the platinum solution, and you get, instead of lead around ruthenium, you get platinum around ruthenium. It depends whether you use platinum 4 or platinum 2, the ratio between lead and platinum can make a difference in terms of the thickness of this platinum layer around ruthenium. And it turns out this is the most active catalyst for carbon monoxide oxidation by far. To not go to show you how good it is, I just want to give you an idea that the regular catalyst starts oxidizing CO somewhere around 600, and we start to see oxidation happening around 0, which is about half a volt shift, that's why it become cover page in a special edition of Social Science related to plants, because we just blew up the whole community. And obviously now you understand that, you know, size is important, but can we do something else about this? Can we narrow the distribution? Can we design clusters to be exactly the size like lithography and stuff? All right. So it turns out you can create some networks on the surface which are made of supramolecular templates, which are two-dimensional structures self-assembled on the surface, so you don't go in a clean room and do lithography. You just put this in a solution and it takes care of this. And it turns out if you use this as a templates and you do SLRR through these templates, you can end up with having beautifully, almost unbelievably well ordered and same size platinum clusters, right? If you do this to certain different templates like this by pyridine, you get these elongated platinum clusters. All right, and remember, this is how it looks like if you don't do too many templates and so on. And this is how it looks like if you don't do SLRR, but you try to deposit platinum anyway, okay? Just for you to refresh your memory. Okay, let's go back. Let's see. All right, so. Okay. Now, I guess I convinced you why we need to worry about the cluster size, right? Okay. If you remember, some time ago I talked to you about nucleation kinetics. And I said that nucleation density, which is the number of nucleus per unit area, N, is equal to F, which is the flux
over d of the whatever, let's say dp, surface diffusivity of the particular a square, particular n on the surface, and a square is the interatomic space on the surface, or distance for a diffusion Hall, right? All this on power 1 over 3. Do you remember that or not? Because if you don't, you're gonna have some major trouble doing your homework. I hope you guys read the material I send you, and if you don't, again, trouble is for you. Alright, so we can say that this is proportional to some constant, which is going to say 1 over dp a square on power 1 over 3 times f on power 1 over 3, okay? F is the flux, how much you're getting things on the surface. Okay, so let's think about our case here. What we have, again, I'm going to rewrite this thing, is the theta m on s hkl upg plus dp plus goes to p over s hkl plus m plus. All right, so let's take care of the stoichiometry immediately. So this is all right. P plus is the stoichiometry coefficient that basically this is the charge of this, and that means that the charge of this side has to be equal to the charge of this side, and this is going to be only if we have here P plus or P over M ratio, okay? Let me just see if I'm going too fast, but I should. Yeah. And this is again have to be here to P over M. So your oxidation state of your ions is basically the stoichiometric coefficient, right? Now that's the first thing. The second thing, obviously, because this theta is here and this is here, then I'm sorry, this is supposed to be like this P over M here. So this. But because I have this theta here, then the theta will be here too. Okay? So as much coverage I start out of my UPD metal monolayer, that much coverage times this ratio here, I will get of my catalyst on the surface, right? So that's the full stoichiometric relation of this business we're talking about here, right? Okay. Or if you want to know more details, you could say that theta P is equal P over M theta M. That's another way of looking at this. Right? All right. Actually, it's M over P. All right. Okay, so I'm interested in flux. Now think about this. How quickly I change the coverage of N, that how quickly I'm depositing P, right? Do you understand that? How quickly I'm dissolving M, that's how quickly I'm depositing P. That is pretty much linked by the reaction. What that really means is that minus d theta over dt, meaning reducing the coverage of the UPD layer, and I'm going to call this M, is equal to d theta over dt of P. But
it has to have this constant, you know, that factors the stoichiometry direction, so it has to be times m over p, just to make sure that we know what we're talking about, right? But you're not gonna get 1 to 1 atom unless this ratio is 1. If let's say platinum is 4 plus and copper is 1, you need 4 coppers to get 1 platinum. That's why this will be 1 over 4, because for 1 copper you're gonna just get a quarter of the platinum coppers, right? Do you understand? Right. That's a very simple thing. But the bottom line is that you do get an idea the speed of the deposition or flux. Now, this is still not flux because it's dimensionless, because this has unit of nothing, you know, color. To make it flux, we need to convert this to some kind of a surface concentration of the UPD layer. So I'm gonna multiply this G monolayer, and here will be G monolayer. What is that? That's the surface concentration of the full UPD layer. Okay? In terms of atoms per centimeter squared. Okay? Or if you want, it could be moles per centimeter squared. Doesn't matter, the atoms, you take Avogadro's number and you get moles. So we need that conversion to get the units of flux, which is either atoms per centimeter squared second or moles per centimeter squared second, all right? So we can say now that our flux is equal to a G monolayer, m over p times d theta over dt, okay? Now, d theta over dt, what is that? Or if you think about G monolayer times theta, that is equal to basically surface concentration CS of the M, right? Because this will give you either moles or atoms per unit area when you multiply these two, right? Coverage is just a thing what you start with, right? Now, if you go to chemical kinetics, which some of you have never done, the easy way to express this basically dC over dt is using the regular theory of the chemical kinetics, is some constant K, which is constant of SLRR, times the concentration, okay? That's the way we do it, okay? And to be the more general thing, I'm gonna say that dC m over dt is equal to K SRRR times Cm on the surface. Or if we are just candy and we get rid of the C and you use GML, and here becomes theta, then this becomes theta and GML, right? And we can get rid of that, okay? You see that or not? So the d theta over dt, using some regular chemical kinetics analogies, constant of the rate constant of the reaction times theta. Now, to complicate a little bit, this theta, if it's a power 1, that's the reaction of the first order in terms of the UPD ions. If this is power 2, the reaction is the second order in terms of the UPD atoms. And if it's a 3 or 4, so the order of the chemical reaction is not necessarily clearly explained to you, but it has to do something with molecularity. And molecularity, again, people don't mention too much, but I'll tell you what it is in general. Like let's assume we have a copper plus PT4 plus goes, this is copper UPT, goes to copper 2 plus PT, right? Because this is 2 plus, then I need two coppers to react with one PT, right? So 2 coppers react with one PT. So, in the statistical mechanics sense means that 2 coppers that I have on the surface has to somehow get at the same time in the moment and space in collision theory with PV. And that means this reaction is a second order in terms of the copper. In very simple way. Usually this is not so simple, but I'm trying to give you an idea what the order of the reaction is. If this would be a copper 1, so copper plus, then I would need 4 here and 4 here. That would mean I need 4 coppers. And then the reaction order would be 4 in terms of the copper UPT. Okay? Now, if I use the platinum 2 plus and I use the copper 2 plus, then I would have 1 copper reacting with 1 platinum, and the order of the reaction would be 1. Okay? That simple molecularity transposed to the order of the reaction, which not necessarily is exactly like this. Simplifying things, because there's a lot of other things that can affect order of the chemical reaction. All right. So this order of the chemical reaction, in the most general case, we will put M. Okay? N could be 1, 2, 3, could be 2.3, who knows? 4, right? Okay, so now we have this defined. So our flux could be written now having this expression as F is equal to G monolayer times M over P times K SLRR, which is the rate constant of SLRR, times theta on M, right? Do you see that? I mean, you're gonna get material, but it's straightforward. We just replace this with this here. And we get this. And then we get this. Okay? It's a simple math when you read material. It's not a big deal, like it's a Mickey Mouse. Having that was eureka moment for me. I said, wow, man, I'm so smart. Nobody knows better than me. That lasted for a short time. Now, if you look this, by the way, and you look at the nucleation density expression, which is given here. Right? So let me just try to save some space. But anyway, if I write nucleation density right now, N is equal to, I have F on power 1 over 3, which means all this will be on power 1 over 3. Then I have 1 over dp a squared. And then I can put this M over P, K SLRR, GML, so GML, M over P, K SLRR, all to be on power 1 over 3, and times theta on the UPT monolayer that we start with on power N over 3. Okay? So that's my nucleation density. And I should be able to smartly change this from becoming 1 to 0.8 to 0.6 to 0.4, etc., etc., do the reaction, and then go and now count the number of clusters I get. And I could actually fit my number of clusters, so nucleation density, as a function of theta, and I should be able actually from this relation to come up with the exponent and extract the rate of the order of the reaction, right? And I would be able also to get this constant too, right? Okay, I thought I was smart. I get some good student too. And this is the theta, this is 0, this is 1. And we started these measurements, and this is n, units in 1/centimeter squared. And we started with 0.1, or actually 0 is, let's say 0, 0.1, 0.2, 3, 4. And you know, each time he runs the experiment, he brings me the data and I plot, and everything, you know, increases according to this. This is the rising function, right? Monotone rising, right? Oh man, I'm looking phys lab later. But as soon as it crossed 0.6, I think, if I remember, bang down, bang down, bang down. I said, what's going on, man? You're not doing this right. You know, I start getting irritated. Let me see the images. Are you doing correct processing of the images? Because I thought this thing here, initially I thought, is because the clusters are merging. And so instead of counting 3 clusters, you know, because the number of clusters per unit area increases, I thought is counting 1, and that's why we're getting this down. But because we get reaction where we have PT4 plus and over P plus copper UPD goes to PT0 and basically, you know, plus copper plus, then this ratio M over P is a 1/4. So this is also 1/4. So even if I have full coverage of the copper, I should only get 25% coverage of the platinum due to the stoichiometry. So I knew that the experiment design should not ever bring me in a vicinity of this problem. But I didn't know, you know, I said, you know, let me see, I was angry, I said, repeat, I bought a new crystal. So it lasted about 6 months. And this just got better. It got phony, right? So it's not monotonic function as I predict in this small model here. It's rising function, but it's a bell function, it looks like this. And when this is so reproducible with 2 different crystals, with a student who's super diligent in work, and I'm, you know, a person who yield if you convince me with strong data. If you blah, 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 and try to convince me, it doesn't work. But after 6 months, he convinced me with the data, this is what it is. And, you know, I didn't want to publish this without some appropriate interpretation, and my student graduated and left, and he was pissed off because I was delaying the publishing of this paper. And I was thinking. Then I realized there's something else. And this kinetics of nucleation that we discussed here, this comes from the statistical mechanics modeling data in the vacuum. And what this really does, it does basically, it's unhindered type of the diffusion problem where you have a surface and the atoms come from the vacuum phase and come down here, and based on their diffusivity, they will eventually meet each other and nucleate. But the surface is homogeneous in that sense; it's on the substrate. Here, what we have is the surface that has UPT metal, which is actually reducing agent. So we have two scenarios. And actually, I have to tell you guys, sometimes dreaming is a good thing. If you dream, you can dream your solution. So what happens here? The first scenario is that you have some free substrate surface, and reduced platinum atom lands on the free surface, diffuses around, meets another one on the free surface, and nucleates. This is where this model applies, right? And if this is the case, no problem. But the rest of the surface is covered with UPD atoms that are still there. The platinum atom can actually land not on this portion, but can land on the other portion which is covered by the UPD. And it can diffuse it and eventually incorporate in some kind of a defect site, some missing portion of the UPD, right? Like what is on the picture. And then as you gradually start removing the rest because you're reducing, this guy will become free and eventually join the existing nucleus. So it's likely to be more involved in the growth part of the deposition rather than into nucleation. So basically my nucleation event is not proportional only to the flux, but it's also proportional to the probability, spatial probability of the nucleation on the free surface. And that's why the model, as you can see, is equal to some alpha constant, which I already described, 1 minus theta times theta of n over 3. Now here, before this theta, there will be a certain constant, psi. And this constant by default is some finite tiny probability of nucleation for the situation when the theta is equal 1. Okay? Because if the theta is equal 1, then there will be still some nucleation density, and it will be equal to this psi factor. By the way, this psi is really small, 0.0009, which means you would get very, very few nuclei at 100% coverage. All right. Now, this is the model, and if you do the math, it perfectly fits data. Okay? How we do with the time?
I think it's 60.
60, excellent. If you fit this to that, this is what you get. The more important part is that you can extract the value of this constant alpha. To remind you, this alpha is equal to G monolayer d p, which is diffusivity A p squared m over p times k SLRR or 013. Okay. Now, without going into much details about the math, I assume you do understand that this factor n, which is the order of the reaction, which I explained to you what it is, does control the position of your maximum. if the N is bigger, what happens with the maximum? My electrical engineers, which way it shifts? This way or this way? Okay, let me ask you this. This is one. And ignore this for a second because it's, where would be the mass? Five, right? This is 2. This is still 1 minus theta. Where would be the mass?
0.75.
Point. So you say increasing N
Is real.
right, okay. All right, the bottom line is this. Choosing certain kind of a chemistry of the solution which allows you to control, to some extent, alpha through NP ratio, but more importantly, through order of the reaction, as we discussed, does affect what coverage gives you the maximum nucleation density. Or, let me translate this to you. If this is the SP, which is the average size of the cluster, size of the P cluster is 1 over NP, right? If you remember this relation, because number per, this is the size, this is the number of clusters per unit area, and this is proportional to 1 over this, right? So this is the size. So if I have this, then I would have this in terms of the P clusters as a function of theta. So the clusters at this coverage, which gives me the maximum nucleation density, will be the smallest for my catalyst, the lowest activity, right? If I go towards full coverage or lower coverage, I will be increasing the size of the cluster, right? That's why you need to know something about this, right? Okay, so that means that this N could be designed by you by choosing the appropriate chemistry, especially with platinum and copper. We have opportunity. Copper could be stabilized in copper plus, copper 2 plus, platinum could be plus 2 or plus 4. Based on that, you can play with this and figure out that you're not getting always the same type of the catalyst because the clusters are not the same. And that's what happens to me Monday versus Wednesday. Monday, I don't even look, I make platinum solution, platinum 4, whatever. Wednesday, I become a little bit more prudent and I make from platinum 2 plus. Suddenly, wow, 2 different catalysts. Just by controlling the chemistry, because you control N. But what is really important here, look at this alpha. Let's say I fix my theta, and I'm here, or let's say I fix my theta, I'm here, which means this, 1. Can I make the cluster smaller or bigger? Well, if this alpha is big, what happens to this curve? Goes like this, right? Alpha increases. What happens to this curve? Well, I mean, I already made this super small, but let's say if this becomes this, right? So, in another word, big alpha, small cluster for a fixed coverage. The question is, can we control alpha? Obviously, this is a order of 10 to the 15 atoms per centimeter square. There's a little change you can do whether you choose lead, copper and so on. M over P, that can range from 1 over 4 to 1. So obviously you see this is like going 300% difference depending on the choice of the UPD coupled with the metal that you're depositing. This I'm going to discuss in a moment because that's the key of the whole lecture. And this is the related to the substrate, so not much you can do. And this is the K, this is the constant, which is related to the rate of your reaction. Okay? So I can do something about this and do something about this, which also is tied to N. Alright? But since this is a 1/3, which means it's a third root, or whatever I do here, if you think about increasing something 10 times, or changing 10 times, square root of 10 is what? Genius. Yeah.
400.
No, it's not 3, for sure. 2 times 2 is 4, times 2 is 8, 3 times 3 is 9, times 3 is... So it's between 2 and 3 for sure. So if I change something here in terms of this 10 times or decrease 10 times, because it's a third root, the net change in terms of alpha will be of order of, 200 to 300%, right? 2 to 3 times. Is that a fact? Yes. So what that means, 2 to 300%, when it comes to this, I can change the cluster size by taking care of this 2 to 300%, because 10 times faster reaction is easily achieved, as you will see. Or 10 times slower reaction. Depends what kind of catalyst you want. Whether you want catalyst with small clusters or big clusters. Sometimes you want to hinder activity of the catalyst because it does gets poisoned very easily by the product. Then you make smaller clusters. If you want to just activity, you have no problem with the intermediate products gluing to the catalyst surface, then you go big clusters. You want big clusters, you make this small. You want small clusters, you make this big. Okay? Everybody on board with this? On the end, I'm not going to go into too much of this story, but this K of the SLRR is equal to the fundamental rate constant K times the surface concentration of the P and the surface concentration of the M plus, P plus. Those are the concentration of the ions. And it turns out I can easily change this 10 times if I use 10 times higher or lower concentration of this, 10 times higher or lower concentration of that, and then temperature could affect the fundamental rate constant. But the bottom line is, if you know what you're doing, you can perfectly design your catalyst to be optimum size or optimum morphology and so on, right? Because this is your KSLR, okay? All right, now what I didn't tell you is why this really works. Why is this 2D? Well, it turns out when you do model fit and you extract this alpha, you can get the value of the diffusivity of your depositing atoms, which in this case, let's say it's platinum. And it turns out that the diffusivity of platinum that comes out from the model to the experimental data, which is not directly measured but indirectly, is about 3 to 4 orders of magnitude higher than diffusivity of platinum of the same substrate measured. There's no techniques to measure this. But during this reaction, it turns out platinum is super fast on the surface. And if it's something super fast on the surface, just looking this, turns out it promotes 2D growth. If you remember mediation and all this stuff, one of the ways to force 2D growth is to increase diffusivity on the surface, which means you go up with the temperatures. Here we don't go up with the temperature because inherently platinum diffuses super fast during this deposition process. Now, why does that? That's something that should be researched, but here's one explanation. Let me see. What happened? When platinum atom comes down, it is likely, and this is already known, that can form a dimer with a lower melting temperature and higher diffusivity, copper or lead or whatever it is, serving as you believe. And that dimer actually can move way faster than the single platinum atom. And this is the reason why this grows too deep. It's hard to prove, but some friends of mine did Monte Carlo simulation, and the only way they can get a Monte Carlo simulation is either to model this with a dimer, or just simply put this to be 3 or 4 orders of magnitude higher. So I was lucky a little bit, but I was also right about doing it. And we got to the position of platinum. Super controlled process. You can design cluster size, you can design reactivity with catalyst based on morphology. All this stuff is not perfectly well understood. Now, having said that, just to give you an idea here, is that you can see that having the same concentration of platinum in the solution, you can change the reaction rate constant from being transport limited, which is 2 times 10 to the minus 3, if you start mixing, to about 0.1, which is about 100 times. Square root of 100, third root of 100, Peter, what is it?
Third root?
Of 100.
That's less than 10.
Of course.
I would say it's
about
even
4.
less than
It's
5.
4
It's
point
4
something.
point, yeah.
So you can change 400% cluster size going this way or this way, depends what your idea about cluster size is. Whether you go bigger clusters or smaller clusters, by just controlling the mixing rate. Here at 1000 RPMs, there is no mixing rate. For example, this is something that, for example, is fairly easy to do. Here, for example, is an interesting showing you that if I just keep changing the concentration of here's the gold deposition, but doesn't matter, here's the rate constant, and you can see by just increasing the concentration of gold, I can change the rate constant from being about 0.025 to being 0.25, which is about 10 times. Or increasing the gold concentration about 5 times 10 to the minus 5 to about 5 times 10 to the minus 4, 10 times, right? It's straightforward. It's a first order reaction in terms of the torque. On the second one, interestingly enough, as I told you, if you have a lead or UPD ions in the solution where you have SLRR, which we initially thought we don't need because thermodynamics tells us we shouldn't. You can see the more lead you have, the faster reaction is because the rate constant is bigger. Now, it took me a while to understand why that. So how easy you always do that. It turns out it has to do something with the activated complex theory and Marcus charge transfer rate theory. And I'm not going to bother you, but I just want to tell you that this is well understood. And it's shown here where this is reorganizational energy. These are concentrations of the metal depositing in UPD ions, and so on, but you can see that this explains really well, because this equation for K is what you see here, the straight lines are basically modified to the data. And also another thing is interesting, which is super cool, because you can change the rate of the chemical reaction by changing the concentration of the supporting electrolyte. And that has to do something with the bi-Hickel theory and shielding of the charge by the electrolyte and the bi-length, etc. I'm not going too much into theory because this is not physical chemistry related course, but the position, but it turns out even that is well understood. There is an equation that pretty much tells you how the rate constant, fundamental rate constant, depends on the concentration of the supporting electrolyte. So you can even do that. It's super easy. 1 molar per chloride versus 0.1 versus 0.01. 100 times change will give you a big change in the rate constant. And this is the end of this lecture, which could be much longer. I could teach half of the semester just this, but I don't want to, because I try to teach you some other stuff. But whether you're going to get this, that, this, and what kind of chemical activity or catalytic activity of this monoelectric have is directly proportional to your knowledge about this deposition method and catalysis, of course. And it's not a Dissonian science where you just get something and say, wow, and write a paper and say, we did that, we got that. Isn't that nice? Those kind of papers you throw in the trash, because there's nothing new for you to learn from that, instead of just, reading the recipe. But if the paper says, we got this data because there's a link in the theoretical, work where it predicts this, and this is because of that, and then it means you have some brain when you do it. All right. So for that reason, this is how I teach this class, to stimulate your brain rather than to stimulate your skills on Google, right? Okay, so that's pretty much it. I'm done for today.